Okay, so our next and final talk of this session is Beyond Backtracking Connections in Fine-Grained Concurrent Separation Logic. It's going to be given by Mulder.
Yeah, thanks. So my name is Ike, and today I'll talk about our paper Beyond Backtracking Connections in Fine-Grained Concurrent Separation Logic. And the setting is somewhat similar to the previous talk. We're trying to verify programs that have fine-grained concurrency. So here you should think of lock implementations, of reference counters, and of concurrent data structures, such as stacks and queues. Now, the setup of such a verification, what you need to do is you need to provide the implementation. You need to give some specification, what you wish to show about your program. And since you will have, or you may have multiple threads that operate on the same piece of memory, you need to write down some kind of invariant on the shared state. Now, what you hope is that you take these three ingredients and you feed them to some tool that will then mix these up and construct a proof that indeed your program satisfies this specification. And the tricky part that the tool needs to do is to use this invariant. So when you're accessing some piece of shared memory, the tool needs to use the invariant to show that accessing this memory is okay. And if you're changing this piece of memory, you need to show that the invariant is still maintained. So let's look at some verification we could carry out, namely that of a reference counter. So a reference counter is used to safely give multiple threads read access to some kind of resource. And it does this by keeping track of the amount of read access tokens. So you have some location which does this keeping track. It starts out maybe at some value 1, and if you want to give another thread read access, you increment this location. Once you're done, you can decrement it again, and once all threads are done, the location is will now point to 0, and the resource can then be used again by the last thread. Okay, so the point here is that if we want to automate the verification of this reference counter, we really need to deal with this invariant that has the shape of a disjunction. So I've written this quite suggestively because the shape of disjunctions appears throughout such verifications. So we take this reference counter, and there are several tools available to verify it. So there's Starling, there's Voila, there's Caper, and there's our own tool, Diaphragm. And the problem here is that all these tools kind of need some help for verifying this reference counter. And that's really because they struggle with the disjunctive nature of the invariant. So what's their approach when they see such an invariant? Well, they typically use backtracking proof search to try to find the correct side of the disjunction to restore. But that does not suffice for the reference counter. So then these tools need to fall back to proof annotations in some shape where you would rather have the tool do it all automatically. So our work is kind of a new approach to proving these disjunctions that's based on connections. So by finding a connection from a hypothesis to our goal, we can infer the correct disjunct. And we took this approach and extended the diaphragm tool and then evaluated this on 24 examples. 14 of these we can now verify fully automatically, so that's an increase of 7, and the proofs became about 30% shorter overall. So for the remainder of my talk, I want to try to explain to you how this connection approach works a bit. And we'll look at an example for that. So this example exhibits kind of the key difficulties that make the verification of the reference counter hard. So what we have is we have some number m, it's between 7 and 13, it's 0 modulo 5, and we now wish to prove that if our location L points to this number m, then it either points to 10 or it points to 15. Now, of course, the only number in this range that is 0 modulo 5 is 10, so the entailment holds. But now we want to try to show this automatically. So we'll first look at how backtracking proof search works again, and I'll try to convince you that in our setting, it's really something you rather not have. Then we'll slightly tweak the example, make it a bit more difficult. Then we need to do a case distinction, which makes the problem a bit harder. Then we can demonstrate our idea of finding connections from hypothesis to goal, and then I'll say some short words about the implementation and evaluation. So backtracking proof search, what's that again? This is the approach taken by the old version of diaphragm and also by the caper tool. Basically, when you see a disjunction as your proof obligation, you just try the left and run your proof search on it. Now, at some point, this will either say solved, in which case you're happy and you're done, but most often you will be in the unsolved state and you need to go all the way back to your original disjunction and try the right branch. So let's see what happens on our running example. So we choose the left-hand side, which is the correct side, and then we hope that our proof automation has some simplification step, turning the entailment L points to M to L points to 10 into just proving that M equals 10. Now the remaining proof obligation is a simple integer equality. So you would hope that any proof automation tool is able to handle this easily. But suppose now that your automation cannot do this. So in this setting, obviously it makes no sense, but you will have maybe equalities on lists or have nasty quantifiers lying around. So you will often have the case that your proof automation system is not good enough to show this. So for the purpose of this talk, let's assume you forgot to load support for modulo reasoning. This is actually something that can happen in the Coq proof assistant, so it's not entirely made up. So what happens then is that the proof just fails. You cannot distinguish this. You cannot distinguish the proof automation is not good enough from this entailment does not hold. So the proof will fail and will backtrack to the right-hand side. And this entailment is, of course, false, so we cannot prove it. And so the goal is left unsolved. Now for the user, this is really kind of bad. We had some entailment and just no progress was made. The reason of failure is unclear. You get maybe something like all branches failed, and there's no easier goal that is left for the user to inspect and see what they can do. Now let's slightly tweak our example and make it a bit harder. So now we change the range. M is now between 7 and 18. Suddenly there's two numbers which M could be, 10 and 15. So now if we do backtracking proof search, first try the left-hand side, this entailment is false because M could be 15. And if we try the right-hand side, we get the same problem. So the backtracking proof search approach does not work. What we need to do is we need to do a case distinction on whether M equals 10 or M equals not equals 10. Only then can we pick the correct side of the disjunct. Now at this point you might say, okay, well, doesn't classical logic kind of fix this? And indeed, in classical logic you have a kind of a better rule for choosing the sides of a disjunct, namely that you can get to assume the negation of the right-hand side if you want to prove the left-hand side. And that would really be quite nice, and that would help us fix this problem. However, if your separation logic is advanced enough, it becomes incompatible with classical logic. So if you're modeling garbage-collected languages, or if your separation logic is step-indexed, which facilitates reasoning about recursive programs, then your separation logic can no longer be classical. So this means we really need to think of something else. So this brings us to our idea of finding connections from hypothesis to goal. So in classical logic, we don't have this problem with case distinctions, but of course in intuitionistic logic, we do. And so we looked at the literature there and found something called connection calculus, which is already from the 90s. It's a complete proof search procedure for intuitionistic logic and is used by, for example, the Eileen Kopp solver, which is one of the top solvers for intuitionistic proofs, entailments. And how it works is by kind of finding connections. So if we have the entailment shown on the slide now, it looks at the C in the disjunct in the goal, and it notices that the C also appears kind of in the implication of our hypothesis. And it uses that to decide, hey, maybe it's a good idea to first eliminate this implication before we choose a side of the disjunct. Now, connection calculus, it's complete, but it's kind of hard to port this directly to other logics. So we kind of took the idea of it and changed it up a bit so that it was more easily portable to different logics. So we still have this idea of finding connections between hypothesis and goal, but now we have an incomplete set of rules that guide the choice of disjunct. So you can do this for intuitionistic logic. You can also extend it to our setting of separation logic. And we found that this set of rules is useful in practice to guide this choice of disjunct. So let's see how this works. So we have our running example again, where L maps to L points to M, and we wish to prove L points to 10 or L points to 15. Our approach looks at these two highlighted resources and thinks about this and sees, hey, well, there's kind of a connection between these two resources. Namely, if we prove that M equals 10, then the entailment holds and we would be done. Now, instead of committing directly to this left disjunct, what we do is we replace this M equals 10 side condition and we put it inside our goal. But note, our goal is still a disjunction, so we keep open the possibility of still choosing the right disjunct. Also note that the L points to M resource, it disappears from in front of the turnstile, and instead it shows up now in the right disjunct. So this is a consequence of separation logic being substructural. We really need to remove it from our context, but we can still recover it in our right disjunct. Now, our goal is still disjunction, and so we can apply our approach again. So we're looking for a connection to M equals 10. And M equals 10 is something where we have kind of, we can have the law of exclude middle here. So we think, hey, we could have M equals 10, we can do a case distinction now. In the case where it's true, we prove the left disjunct, and in the case where it's false, we can use that information to prove the right disjunct. Now, this remaining proof obligation should really be quite simple. And in the case where we did forget to add support for modular reasoning, we get this remaining proof obligation. This is still relatively simple, but it's much more useful maybe to the user, since you can just see, oh, hey, we forgot to add support for modular reasoning, and then solve this goal manually. So let me say a few words about the implementation and evaluation we did. We implemented our approach on top of Diaframe. Diaframe is a proof automation library for the Iris separation logic framework in the Coq Proofs Assistant. We evaluated this approach on 24 examples, 14 of which we can now verify automatically. That's 7 more than before. The proofs have become about 30% shorter, and this is something I really like, is that the proof search no longer relies on backtracking for all but one of these examples. So this really makes the debugging process of figuring out why a proof failed much better for the user. Our artifacts are available and they have been evaluated as reusable, so we're happy to try those out. So in conclusion, we looked at verifying programs with fine-grained concurrency. To do this automatically, we need to be able to reason about invariants that have disjunctions. And this talk is about a new method for automatically proving such disjunctions, namely by finding a connection from hypothesis to goal. And with that, I'm happy to take any questions.
Hi, I'm Alay Sergey from National University of Singapore. Very nice talk and very elegant methods. Doesn't have that much to do with fine-grained concurrency per se, right? Okay, so more substantial question. Have you thought of using that for invariant inference? So because one of your first slides showed that part of the specification is an invariant for the fine-grained data structure. Yeah, on the shared state and Gauss state, I presume. And I was kind of hoping that you would say that this paves the way towards inferring those invariants somehow. Can you say something about that?
Yes, I have really not thought about inferring invariants with this method. I'd be happy to talk about it later, but I have no idea how to do that. Yeah.
Well, you might look at the approaches based on effectively propositional reasoning that people use for distributed systems. I wonder if there is any relation. We can discuss that. Thank you.
Yeah, let's discuss.
Hi, Peter Müller, ETH Zurich. I'm wondering, have you considered implicit dynamic frames as a variation of separation logic? Because it seems that if you separate the value reasoning from the permission reasoning, then you can just use traditional predicate logic to resolve these kind of disjunctions.
Yes, so I've thought about this a bit, and indeed that works for some cases, and for this case it would work. However, it doesn't work for all cases, so let me see if this works. So if you consider the same reference counter, but now you're gonna free the last, upon doing the last decrement, you're gonna free this location. And then you really don't have any state to do this case distinction on. So if you consider the reference counter with free, you cannot get away with doing the case split with pure reasoning, if that makes sense. So it really, you really need to look at the resources and see what you have before you can make an informed decision on the case splits in general.
Yeah, possibly. You might be able to use a ghost variable to do that, but we can take that offline. Thank you.
Sure.
So with the diaphragm stuff, with this, can you verify anything new, or is it you've sort of basically done the same proofs but in a much more compact way? Is it?
I think with enough proof annotations, you can still verify the same things. The thing is that some of these verifications really can now go through automatically, so you really don't need to touch the Coq proof mode.
So from a automation point of view, like typically whenever I've done something that's automated, it's failing, and then automated. So how long does it sort of take you to go from it not working to it being automated?
Good question. I think it would also differ on how long you have used the tool. So for me, because I'm familiar with it, like verifying a reference counter can be done in the scope of a couple of hours, I think. Writing down the invariants is usually the difficult part. If you're less familiar with the tool, yeah, that might take a bit longer.
Cool.
Jean Pichon, Aarhus Universiteit. I have a sort of nested question, which is, so you mentioned these fine-grained concurrent data structures. Have you thought about looking at relaxed memory? And in particular, there's a bunch of separation logics for relaxed memory that use state transition systems to keep track of the state of things, in which case you have lots of disjunction reasoning to go like, am I in this branch of the state transition system or that other branch? Am I in between that state and that state? And if so, do you have any results on that?
I don't have any results on that.
Or thoughts?
So I have thought a bit about, or thinking a bit about applying diaphragm in a weak memory setting. We're very much still exploring how that will work. I think most disjunctive reasoning about these state transitions, my intuition would be that you could use this approach to help you guide the choice there, definitely. Even though there might not be an explicit disjunct, you could try to make it more explicit in the automation, and then it would help you there, I think.
Okay, cool. Thank you.
Cool. Okay, so we now have a break until 11:20, I think. Coffee break, but let's thank the speaker for a wonderful talk.